maybe another distinction we want to try to get at is the difference between fission and fusion. So you mentioned fusion is the kind of reaction happening in the sun. So what's fission and what's fusion?
Sure. Well, fission is taking heavy elements like uranium and breaking them up. And it turns out that that process of breaking up heavy elements releases energy.
What does it mean to be a heavy element?
It means that there are many nuclear particles in the nucleus itself, neutrons and protons in the nucleus itself, so that in the case of uranium, there are 92 protons in each nucleus and even more neutrons, so that the total number of nucleons in the nucleus, nucleons is short for either a proton or a neutron, the total number, might be 235, that's U-235, or it might be 238, that's U-238. So those are heavy elements. Light elements, by contrast, have very few nucleons, protons or neutrons in the nucleus. Hydrogen is the lightest nucleus. It has one proton. There are actually slightly heavier forms of hydrogen, isotopes. Deuterium has a proton and a neutron, and tritium has a proton and two neutrons, so it has a total of 3 nucleons in the nucleus. Well, taking light elements like isotopes of hydrogen and not breaking them up, but actually fusing them together, reacting them together to produce heavier elements, typically helium, helium is a nucleus which has 2 protons and 2 neutrons. That also releases energy, and that or reactions like that, making heavier elements from lighter elements, is what mostly powers the sun and stars. Both fusion and fission release approximately 1 million times more energy per unit mass than chemical reactions. So a chemical reaction means take hydrogen, take oxygen, react them together, let's say, and get water. That releases energy. The energy released in a chemical reaction like that, or the burning of coal or oil or whatever else, is about 1 million times less per unit mass than what is released in nuclear reactions.
But it's hard to do.
It requires very high energy of impact. And actually, it's very easy to understand why. And that is that those 2 nuclei, if they're both, let's say, hydrogen nuclei, one is, let's say, deuterium, and the other is, let's say, tritium, they're both electrically charged. And they're positively charged, so they like charges repel. Everyone knows that, right? So basically, to get them close enough together to react, you have to overcome the repulsion, the electric repulsion of the 2 nuclei from one another. And you have to get them extremely close to one another in order for the nuclear forces to overtake the electrical forces and actually form a new nucleus. And so one requires very high energies of impact in order for reactions to take place. And those high energies of impact correspond to very high temperatures of random motion.
So that's why you can do something like that in the sun. So we can build the sun. That's one way to do it. But on Earth, how do you create a fusion reaction?
Yeah. Well,
engineering-wise,
nature's fusion reactors are indeed the stars, and they are very hot in the center, and they reach the point where they release more energy from those reactions than they lose by radiation and transport to the surface and so forth. And that's a state of ignition. And that's what we have to achieve to give net energy. It's like lighting a fire. If you have a bundle of sticks and you hold a match up to it, and you see smoke coming from the sticks, but you take the match away and the sticks just fizzle out. That's not the reason they fizzled out. Is that yes, they were burning, there was smoke coming from them, but they were not ignited. But if you are able to take the match away and they keep burning and they are generating enough heat to keep themselves hot and hence keep the reactions going, that's chemical ignition. Well, what we need to do, what the stars do, in order to generate nuclear fusion energy is they are ignited. They are generated enough energy to keep themselves hot. And that's what we've got to do on Earth if we're going to make fusion work on Earth. But it's much harder to do on Earth than it is, in a star, because, we need temperatures of order tens of millions of degrees Celsius in order for the reactions to go fast enough to generate enough electricity to keep it, or enough energy to keep it going. And so if you've got something that's tens of millions of degrees Celsius, and you want to keep it all together and keep the heat in long enough to have enough reactions taking place, you can't just put it in a bottle, plastic or glass, it would be gone, in milliseconds. So you have to have some non-material mechanism of confining the plasma. In the case of stars, that non-material force is gravity. So gravity is what holds a star together. It's what holds the plasma in long enough for it to react and sustain itself by the fusion reactions. But on Earth, gravity is extremely weak. I mean, I don't mean to say we don't fall. Yes, we fall. But the mutual gravitational attraction of small objects is very weak compared with the electrical repulsion or any other force that you can think about on Earth. And so we need a stronger force to keep the plasma together, to confine it. And the predominant attempt at making fusion work on Earth is to use magnetic fields to confine the plasma. And that's what I've worked on for essentially most of my career, is to understand how we can and how best we can confine these incredibly hot gases, plasmas, using magnetic fields with the ultimate objective of releasing fusion energy on Earth and, generating electricity with it and powering our society with it.
Dumb question. So on top of the magnetic fields, do you also need the plastic water bottle walls, or is it purely magnetic fields?
Well, actually, what we do need walls. Those walls must be kept away from the plasma, because otherwise they'd be melted, or the plasma must be kept away from them, inside of them. But the main purpose of the walls is not to keep the plasma in, it's to keep the atmosphere out.
Oh.
So if we want to do it on Earth where there's air, we want the plasma to consist of hydrogen isotopes or other things, the things we're trying to react. And by the way, the density of those plasmas, at least in magnetic confinement fusion, is very low. It's maybe 1 million times less than the density of air in this room. So in order for a fusion reactor like that to work, you have to keep all of the air out and just keep the plasma in. So yes, there are other things, but those are things that are relatively easy. I mean, making a vacuum these days is technologically quite straightforward. We know how to do that, okay? What we don't quite know how to do is to make a confinement device that isolates the plasma well enough so that it's able to keep itself burning with its own reaction.
So maybe can you talk about what a tokamak is?
The Russian acronym from which the word tokamak is built just means toroidal magnetic chamber. So it's a toroidal chamber. A torus is a geometric shape which is like a donut with a hole down the middle. Okay, and so it's the meat of the donut. Okay, that's the torus, and it's got a magnetic field. So that's really all tokamak means. But the particular configuration that is very widespread and is the sort of best prospect, at least in the near term, for making fusion energy work, is one in which there's a very strong magnetic field the long way round the donut, around the torus. Mm-hmm. So you've got to imagine that there's this donut shape with an embedded magnetic field just going round and round the long way. The big advantage of that is that plasma particles are, when they're in the presence of a magnetic field, feel strong forces from the magnetic field, and those forces make the particles gyrate around the direction of the magnetic field line. So basically, the particles follow helical orbits, following like a spring that's directed along the magnetic field. Well, if you make the magnetic field go inside this toroidal chamber and just simply go round and round the chamber, then because of this helical orbit, the particles can't move fast across the magnetic field, but they can move very quickly along the magnetic field. And if you have a magnetic field that doesn't leave the chamber, it doesn't matter if they move along the magnetic field. It doesn't mean they're going to exit the chamber. But if you just had a straight magnetic field, as for example, coming from a Helmholtz coil or a bar magnet, then you'd have to have ends. It would come to the ends of the chamber somewhere, and the particles would hit the ends, and they would lose their energy. So that's why it's toroidal, and that's why we have a strong magnetic field. It's providing a confinement against motion in the direction that would lead the particles to leave the chamber. It turns out that, and here we're getting a little bit technical, but it turns out that a toroidal field alone is not enough, and so you need more fields to produce true confinement of plasma, and we get those by passing a current as well through the plasma itself.
Or to make sure it stays on track.
Well, what that does is makes the field lines themselves into much bigger helices. And that, for reasons that are too complicated to explain, that clinches the confinement of the particles, at least in terms of their single particle orbits, so they don't leave the chamber.
And so when the particles are flying along this donut, the inside of the donut, are they? Where's the generation of the energy coming from? Are they smashing into each other?
Yeah, eventually, in a fusion reactor, there will be deuterons and tritons, and they will be smashing in. They will be very hot. They'll be 100 million degrees Celsius or something. So they're moving thermally with very large thermal energies in random directions, and they will collide with one another and have fusion reactions. When those fusion reactions take place, energy is released, large amounts of energy is released in the form of particles. One of the particles that's released is an alpha particle, which is also charged and is also confined. And that alpha particle stays in the donut and heats the other particles that are in that donut. So it transfers its energy to those, and it keeps them hot. There's some leaking of heat all the time, a little bit of radiation, some transport, and so forth. There's also a neutron released from that reaction. The neutron carries out 4/5 of the fusion energy, and that will have to be captured in a blanket that surrounds the chamber in which we take the energy, drive some kind of electrical generator from thermal engine, gas turbine or something like that, and power the.
And you got energy. So where do we stand?
Where do we stand?
On getting this thing to be something that actually works, that generates energy.
Yep. Well, there have been experiments that have generated net nuclear energies or nuclear powers in the vicinity of, a few tens of megawatts for a few seconds. So that's, 10 megajoules. That's not much energy. It's a few donuts worth of energy. Okay.
Yeah.
Literal donuts.
Literal donuts. That's right.
But we have studied how well tokamaks confine plasmas. And so we now understand in rather great detail the way they work. And we're able to predict what is going to be required in order to build a tokamak that becomes self-sustaining, that becomes essentially ignited or so close to ignited that it doesn't matter. And at the moment, at least if you use the modest magnetic field values, still very strong, but limited magnetic field values, you have to build a very big device. And so we are at the moment worldwide fusion research is at the moment in the process of building a very big experiment that's located in the south of France. It's called ITER, I-T-E-R, which means the way, or just means the International Tokamak Experimental Reactor, if you like. And that experiment is designed to reach this burning plasma state and to generate about 500 megawatts of fusion power for hundreds of seconds at a time. It'll still only be an experiment. It won't put electricity on the grid or anything like that. It's to figure out whether it works and what the remaining engineering challenges are. It's a scientific experiment. It won't be engineered to run round the clock and so on and so forth, which ultimately one needs to do in order to make something that's practical for generating electricity. But it will be the first demonstration on Earth of a controlled fusion reaction for long time periods.
Is that exciting to you?
It's been an objective that has in many ways motivated my entire career and the career of many people like me in the field. I have to admit, though, that one of the problems with ITER is that it's an extremely big and expensive and long time to build experiment. And so it won't even come into operation until about 2025, even though it's been being built for 10 years and it was designed for 30 years before that.
Right.
And so that's actually one of the big disappointments of my career in a certain sense, which is that we won't get to burning fusion reaction until well past the first operation of ITER. And whether I'm alive or not, I don't know. But I certainly will be well and truly retired by the time that happens. And so when I realized maybe some years ago that was going to be the case, it was a discouragement to me, let's put it like that.
But if we can try to look maybe in a ridiculous kind of way, look into 100 years from now, 200 years, 500 years from now, and we, there's folks like Elon Musk trying to travel outside the solar system.
Sure.
I mean, the amount of energy we need for some of the exciting things we want to do in this world, if we look, again, 100 years from now, seems to be a very large amount. So do you think fusion energy will eventually, sometime into your retirement, will be basically behind most of the things we do?
Look, I absolutely think that fusion research is completely justified. In fact, we should be spending more time and effort on it than we currently do. But it isn't going to be a magic bullet that somehow solves all the problems of energy. By the way, that's a generic statement you can make about any energy source, in my view. I think it's a grave mistake to think that science of any sort is suddenly going to find a magic bullet for meeting all the energy needs of society, or any of the other needs of society, by the way. And we can talk about that, I hope, later.
Sure.
Okay?
Yes, definitely.
But fusion is very worthwhile, and we should be doing it. And so my disappointment that I just expressed was, in a certain sense, a personal disappointment. I do think that fusion energy is a terrific challenge. It's very difficult to bring the energy source of the sun and stars down to Earth. This does contrast, in a certain sense, with fission energy. By contrast, fission energy, to build a fission reactor proved to be amazingly easy. We did it within a few years of discovering nuclear fission. People had figured out how to build a reactor and did so, during the Second World War.
Which is, by the way, fission is how the current nuclear power plants work.
Yeah. And so we have nuclear energy today because fission reactors are relatively easy to build. You've got to have, what's hard is getting the materials, okay? And that's just as well, because if everyone could get those materials, there would be weapons proliferation and so forth. But it wasn't all that long after even the discovery of nuclear fission that fission reactors were built. And fission reactors, of course, operated before we had weapons. I think nuclear power is obviously important to meet the energy challenges of our age. It is intrinsically completely CO2 emissions free. And in fact, the wastes that come from nuclear power, whether it's fission or fusion for that matter, are so moderate in quantity that we shouldn't really be worried about them. I mean, yes, fission products are highly radioactive and we need to keep them away from people, but there's so little of them, it's that keeping them away from people is not particularly difficult. And so while people complain a lot about the drawbacks of fission energy, I think most of those complaints are ill-informed. We can talk about, the challenges and the disasters, if you like, of fission reactors. But I think fission, in the near term, offers a terrific opportunity for environmentally friendly energy, which in the world as a whole is rapidly being taken advantage of. China and India and places like that are rapidly building fission plants. We're not rapidly building fission plants in the US, although we are actually building 2 at the moment, 2 new ones. But we do still get 20% of our electricity from fission energy, and we could get a lot more.
So it's clean energy.
So it's clean energy.
Now again, the concern is there's a very popular HBO show just came out on Chernobyl. There's the 3 Mile Island. There's Fukushima. That's the most recent disaster. So there's a kind of a concern of, nuclear disasters. Is that, what do you make of that kind of concern, especially if we look into the future of fission energy-based reactors?
Well, first of all, let me say 1 or 2 words about the contrast between fission and fusion, and then we'll come on to the question of the disasters and so forth. Fission does have some drawbacks, and they're largely to do with four main areas. One is, do we have enough uranium or other fissile fuels to supply our energy needs for a long time? The answer to that is we know we have enough uranium to support fission energy worldwide for thousands of years, but maybe not for millions of years, okay? So that's resources. Secondly, there are issues to do with wastes. Fission wastes are highly radioactive, and some of them are volatile. And so, for example, in Fukushima, the problem was that some fraction of the fission wastes were volatilized and went out as a cloud and polluted areas with cesium-137, strontium-90, and things like that. So that's a challenge of fission. There's a problem of safety beyond that, and that is that in fission, it's hard to turn the reactor off. When you stop the nuclear reactions, there is still a lot of heat being liberated from the fission products. And that is actually what the problem was at Fukushima. The Fukushima reactors were shut down the moment that the earthquake took place. And they were shut down safely. What then happened after that at Fukushima was, there was this enormous tidal wave, many tens of meters high, that came through and destroyed the electricity grid feed to the Fukushima reactors. And their cooling was then turned off. And it was the afterheat of the turned off reactors that eventually caused the problems that led to a release. And so that's a safety concern. And then finally, there's a problem of proliferation. And that is that fission reactors need fissile fuel, and the technologies for producing and enriching and so forth the fuels can be by bad actors to generate the materials needed for a nuclear weapon, and that's a very, very serious concern. So those are the 4 problems. Fusion has major advantages in respect of all of those problems. It has more longer-term fuel resources. It has far more benign waste issues. The radioactivity from fusion reactions is at least 100 times less than it is from fission reactions. It has essentially none of this after heat problem because it doesn't produce fission products that are highly radioactive and generating their own heat when it's turned off. In fact, the hard part of fusion is turning it on, not turning it off. And finally, you don't need the same fission technology to make fusion work, and so it's got terrific advantages from the point of view of proliferation control. So those are four main issues which make fusion seem attractive technologically, because they address some of the problems of fission energy. I don't mean to say that fission energy is overwhelmingly problematic, but clearly there have been catastrophes associated with fission reactors. Fukushima actually is, I think, in many ways often overstated as a disaster, because after all, nobody was killed by the reactors, essentially, zero. And that's in the context of a disaster, a tsunami that killed between 15 and 20,000 people more or less instantaneously. So, in the scale of risks, one should take the view that, in my estimation, that fission energy came out of that looking pretty good. Okay, of course, that's not the popular conception. Okay.
Yeah, it's gonna. I mean, with a lot of things that threaten our well-being, we seem to be very bad users of data. We seem to be very scared of shark attacks and not at all scared of car accidents and this kind of miscalculation. And I think from everything I understand, nuclear energy, fission-based energy goes into that category. It's one of the safest, one of the cleanest forms of energy. Right. And yet the PR, whoever does the PR for nuclear energy is not has a hard job ahead of them at the moment.
Well, I think part of that is their association with nuclear weapons. Right. Because when you say the word nuclear, people don't instantly think about nuclear energy; they think about nuclear weapons, and so there is, perhaps a natural tendency to do that. But yes, I agree with you. People are very poor at estimating risks, and they react emotionally, not rationally, in most of these situations.